Welcome back to day 2 of our PIVOT EIA Training Explainer. Today, we're going to completely transform the way you approach environmental impact assessments. We're talking about taking your EIA reports from instant regulatory rejections to absolutely bulletproof, defensible scientific documents. So if you've ever found yourself scratching your head wondering why perfectly good project data just gets tossed out by regulators, well, you're in exactly the right place. Here's our roadmap for today. First, we'll look at why EIS fail. Second, the top preparation mistakes. Third, scientific interpretation. Fourth, we've got some interactive case studies. And finally, we'll wrap up with the golden rules. All right, let's jump right into Section 1, why most EIAs fail during review. To really get inside a reviewer's head, I love this quote from Francis Bacon: read, to weigh, and consider. You see, assessors aren't just sitting there mindlessly checking boxes. They're actively evaluating your scientific reasoning. Think about it like this. Imagine handing a patient a medical report that literally just says temperature 102 degrees with zero context. No diagnosis, no treatment plan, nothing. Well, that's exactly what a data dump EIA looks like to a reviewer. They don't just want a pile of raw numbers. They desperately need to know the environmental significance behind those numbers. Okay, let's dive into this contrast because it's massive. On one hand, you have the data dump approach. This is where you just list raw monitoring values in a giant table and rely on really weak qualitative claims like, oh, the project may cause some impact. On the flip side, we have true scientific interpretation. This approach actively explains why those values are there. It calculates the relationships between parameters, and it uses strict quantitative modeling to actually predict impacts. Night and day, right? Moving right along to Section 2, top common mistakes in EIA preparation. These predictable traps are literally ruining everything from executive summaries to mapping. Let's look at baseline data first. Too often, environmental monitoring is just treated as a lazy checkbox. We're seeing reports totally missing essential annual and seasonal wind roses. Soil data gets dumped in without anyone ever evaluating actual agricultural suitability. And ecology, it gets reduced to a basic middle school level checklist of plants, completely ignoring crucial metrics like the importance value index. And don't even get me started on socioeconomics. We routinely see massive projects trying to justify their impact using completely invalid sample sizes, like relying on just 43 questionnaires for 4 entire villages. I mean, come on. And those red flags, they march great into the impact and environmental management plan chapters too. Impacts end up dominated by highly subjective qualitative discussions that completely ignore cumulative impacts. Then, the EMP relies on generic, copy-pasted mitigation measures. You know the ones. Statements like, we will plant trees, with absolutely zero scientific backing. Plus, the EMP budgets completely lack detailed CapEx and OpEx breakdowns. And the risk assessments? They're often missing vital quantitative data, like thermal radiation threat zone mapping. It's a mess. When we actually break down the top 20 red flags that reviewers are actively hunting for, a pretty terrifying pattern emerges. Look at this. 14 out of 20 are classified as either major or critical failures. We're talking about severe structural issues here. Things like contradictory water requirements across different chapters, incomplete terms of reference compliance, or totally missing quality assurance documents. Guys, these aren't just typos. These are fundamental breakdowns in scientific defensibility. Which brings us to the cure. Section 3, Scientific Interpretation of Environmental Data. Let's talk about soil analysis. You simply can't just hand a reviewer a table of pH and organic carbon values and call it a day. You have to relate those parameters directly to agricultural optimums. For example, if your available nitrogen is 300 kilograms per hectare, you've got to explain that it falls right into that optimum range of 280 to 560. And more importantly, you need to interpret what that actually means for local agricultural productivity based on the project's specific land use. Now here's an absolutely crucial point. How do you validate your water chemistry data? Enter the mandatory ionic balance check. Here's how it works. First, you convert your cations to milliequivalents per liter. Second, you do the exact same thing for your anions. Third, you calculate the error percentage between the two. And fourth, you have to verify that the balance is within plus or minus 5%. Listen carefully. If that error isn't within 5%, your laboratory data is analytically invalid. Period. Your report will get rejected. When we're interpreting groundwater for irrigation, we always look at 2 critical indices, RSC and SAR. RSC, or residual sodium carbonate, measures the excess carbonates over calcium and magnesium. A high RSC means solid carbonates are literally going to precipitate in the soil.
On the other hand, SAR, or sodium adsorption ratio, measures the proportion of sodium to calcium and magnesium. A high SAR means sodium is going to displace calcium in the clay, which effectively destroys the soil structure and suffocates plant roots. So both indices measure irrigation suitability, but they track totally different destructive pathways.
And this builds directly into the U.S. Salinity Laboratory SAR classification, which is exactly how a reviewer classifies sodium hazards. If your SAR is under 10, great, it's excellent. But if it's over 26, it's completely unsuitable. And here's the kicker. If your water falls into those middle S3 or S4 categories, you cannot just gloss over it in your report. You have to propose mandatory mitigation strategies in your EMP, like soil amendments with gypsum or advanced water treatment.
Moving beyond water, there are strict, non-negotiable quantitative requirements for ecology and air quality too. These require rigorous statistical, trend, and correlation analysis. For ecology, you've got to calculate the Shannon Diversity Index, where anything over 3.0 points to high biodiversity, and the Importance Value Index. As for air quality, no guessing allowed. You must use EPA-approved tools like AirMod for dispersion modeling, and you have to report the 98th percentile to statistically prove you are complying with national ambient air quality standards.
All right, let's put this into practice. Section 4, Interactive Case Studies. Let's kick things off with Case Study A, which I call the data dump. Imagine an EIA consultant presents a table of groundwater sample data showing pH, calcium, magnesium, and chloride values. But there's zero accompanying text explaining these numbers. Put yourself in the assessor's shoes for a second. What's the fatal flaw here? What massive step did the consultant just skip?
Well, the fatal flaw is that the consultant completely failed to diagnose the data. So what's the corrective action? First, run that ionic balance check we talked about to mathematically prove the lab's accuracy. Then, compare those values against IS 10500 drinking water standards. And finally, you have to explain the why. For instance, detail how the local limestone geology is naturally influencing those high calcium and alkalinity levels. The math, combined with the reasoning, that's the diagnosis reviewers are desperately searching for.
Okay, let's look at another classic trap. Case Study C, the flawed impact assessment. Imagine the submitted report literally states, the project will cause some air pollution, which will be mitigated by planting trees. And this brilliantly illustrates exactly what not to do. But what is fundamentally wrong with this statement? The huge, glaring problem? It's entirely qualitative. You can't measure some air pollution. The corrective action here is mandating specific software tools. You absolutely must quantify the air impact using AirMod to show incremental ground-level concentrations. You need to generate noise isolates. You have to conduct a formal hazard identification and quantitative risk assessment using tools like Aloha to plot actual thermal radiation threat zones. You've got to quantify the impact, the magnitude, and the significance. No more guessing. Now check out this terrifying mathematical trap. A consultant calculates a residual sodium carbonate of 143, which would be highly toxic, instead of the accurate negative 2.46, which is perfectly safe. Why did this happen? Because they plugged raw milligrams per liter into the formula instead of converting to milliequivalents per liter first. So what's the consequence of this one little math error? It completely inverts the scientific conclusion. That single mistake could potentially cost the project proponent millions of dollars in completely unnecessary mitigation and water treatment systems. Yikes. Let's bring it all together. Section 5, Golden Rules for High-Quality EIAs. Here is your core philosophy, your golden rules. Number 1, you must validate every single dataset mathematically before you ever begin your interpretation. Number 2, interpret data scientifically. Always explain the why instead of just pointing to a regulatory standard. Number 3, ensure absolute consistency across every single chapter, map, and table. Number 4, maintain total traceability for all your calculations and assumptions. And finally, number 5, always conduct an independent internal technical review before submission. Remember, your EIA is a defensible scientific document, not just a compliance box you're trying to check off. So I'm going to leave you with this provocative thought to chew on as we wrap up day 2. Based on everything we've just unpacked in this explainer, I want you to look at the EIA project you're currently working on right now. Which chapter is the most vulnerable to that data dump critique? And more importantly, which of these quantitative tools are you going to apply today to fix it?